Finally, we have covered the different kinds of gradient descent algorithms, but before we move on to the next types of optimization algorithms, such as gradient descent with momentum, RMSProp, and atom, we have to understand the concept of exponentially weighted averages. Exponentially weighted averages are used in the upcoming optimization algorithms. Let's say we want to calculate the moving average of temperature in the last n days. What we do is we start with 0, and then every day we're going to combine it with a weight of a parameter, let's say beta, times whatever is the value accumulated until now, plus 1 minus beta times that day's temperature. So if we have a daily record of the temperature in London, and we put the temperature and the number of days on the y and x-axis respectively, we can see that when we plot the data, we get this graph, and there are different data points. The purpose of exponentially weighted average is just trying to find a moving average, or a line which goes through the data point that can estimate the temperature in different days. So there might be a lot of noise when we consider each data point, but when we use a moving average, it basically serves as an estimate or a daily average for each data point. And here we need to consider two parameters for exponentially weighted averages. The first one is beta, and beta is used on the formula. So Vt is equals to beta times Vt minus 1 plus 1 minus beta theta t. Theta represents the daily temperatures. On day 1 we have this temperature, day 2, day 3. And Vt minus 1 is basically referring to the previously computed average. So V0 might be initialized to 0. Then V1, Vt will be V0, which is the initial one, multiplied by beta. Here beta is initialized to 0.9, and 1 minus beta will be 0.1 multiplied by theta 1, which is the temperature for that day. And we basically accumulate the averages as we move forward. So on V2 we multiply 0.9 by V1, which is the previous one, computed average, and plus 0.1 multiplied by theta 2, which is the temperature for the second day. So basically the formula can be summarized as Vt is equals to beta multiplied by the previously compiled average plus 1 minus beta times the new sample. In the figure, the red line shows the weighted average if beta is 0.9, and the green line shows the weighted average if beta is 0.98. So in this graph, the red line is indicating when we consider beta to be 0.9, and the green line here is showing us when beta is 0.98. So depending on the type of values that we initialize for the hyperparameter, we're going to have different averages. So beta is one kind of hyperparameter that we introduce besides the learning rate, alpha, which we have introduced previously. By choosing beta value, we control how much weight to give for the last n days in calculating the average. So when we use different values for beta, we basically choose the type of weight assigned to the previously computed averages for the temperature, because it decides the amount that we associate for each value. If we use beta as 0.9, then it's basically considering the last 10 days temperature when computing the averages. How did we get the 10 days from 0.9? We can use the formula 1 minus 1 over beta. Is a simple way to remember how this weight is applied. With beta as 0.9, we will average over the last 10 days of temperature, and with beta as 0.98, we average over 50 days of temperature, and hence average over the 50 days of temperature. So if we choose 0.9 as the weight, then we're just considering 10 temperatures in order to compute the average. If we consider 0.98, then we are computing the average within the range of 50 days, because 1 over 1 minus 0.98 is equals to 50. And if we use a smaller value for beta, we're going to consider the temperature for a smaller number of days. Here we can see the yellow line is much squiggly and mirrors the distribution of the data points. It is to say that when we take the average over a smaller number of days or on a smaller window, it is going to be very noisy because we're considering each day. Imagine that we consider each day one by one when computing the average. That means our average is going to move a lot and it's going to be much noisier. But if we use a higher value for beta, then we're going to consider a larger window when computing the average, and it's going to be much smoother compared to the yellow line, which is the case for the red and green line when using the 0.9 and 0.98 as our values for beta. So in order to summarize, by averaging over a larger window, the average adapts slowly when the temperature changes. This is because a lot of weight is given to the previous value and a much smaller weight is given to the new value. So when we use a much larger window, then a lot of weight is going to be given to the previously accumulated value, and a much smaller weight, which is 1 minus beta, is going to be assigned for the new value. A bit of intuition of how this formula works and why the name exponentially weighted average is given is, as we see, the value of 1 minus beta is what we multiply to the current value. And if we want to expand the equation, we see that we end up multiplying the current value by 1 minus beta and the previous value by beta, which is exponentially decaying on the curve. So what this is basically saying is, when it's called exponentially weighted average or exponentially decaying weighted average, because when we compute the averages over different dates, we're basically considering the one which is previously computed before. So let's say if V100 was this number, then we're going to replace V99 with the one which has been computed here, which is 0.9 theta 99 plus 0.9 V98, and we're going to replace V98 again with the previously computed value here. And what you will see is, when we accumulate all the values, and like when we multiply 0.9 by the values which are inside the bracket and expand the terms, we can see that 0.1 is going to stay fixed, and what's changing is 0.9 is going to be exponentially decaying, which is going to be it's going to be 0.9 at first, and as we substitute more values, then it becomes 0.9 squared, 0.9 cubed, and when we square and cube the values, then it's going to become smaller and smaller, and it's going to decay over time. So that's why the name exponentially decaying weighted average is given for this algorithm. And when 0.9 is reaches the power of 10, it's basically 0.35 and 1 over e. And 1 over e is the same as 1 minus epsilon to the power of 1 over epsilon. So basically what this is saying is it's going to decay, beta is going to decay over time, and exponentially weighted moving average is a highly efficient way to calculate an average. We don't need much memory or compute power to calculate this average. It is also highly suited for machine learning optimizations, and using some form of exponentially weighted average might be helpful over simple gradient descent in neural nets. So the reasons that we are learning about this algorithm is we want to use it in order to improve our simple gradient descent. So we initialize to 0, and then the next value is going to be computed by utilizing the previously computed value. Another thing that we need to consider besides exponentially weighted average is bias correction. Making exponentially weighted moving average more accurate, since the curve starts from 0, there are not many values to average on in the initial days. Thus, the curve is lower than the correct value initially and then moves in line with expected values. So, as you can see, the green line and the purple line are different, but they are for the same beta value. The green line is after considering bias correction, and the purple line is without bias correction. What is happening is, in reality, if we don't apply bias correction when we compute the exponentially weighted moving average over the initial days for 0 days, then we're not going to consider a lot of days for computing the average, so the value will start as 0. But we don't want to start the value as 0. That's why we introduce the bias correction so that it moves a bit upwards to the green line. But as we move forward, we can see that the purple and the green line will overlap over time when we reach higher number of days. But for the initial stage, we need bias correction so that these two could be the same. So the green line is with bias correction and the purple line is without bias correction. So the curve is lower than the correct value initially and then moves in line with the expected values. So the ideal curve should be the green one, but it starts as the purple curve since the values initially are 0. The initial values of Vt will be very low, which need to be compensated, and we can adjust the purple line to the green line by using this formula, which is the computed value Vt has to be divided by 1 minus beta to the power of t, where t is the number of day. So for example, when we compute V2, after computing V2 by using the previous formula, which is beta V1 plus 1 minus beta theta 2, we have to divide it again by 1 minus beta to the power of t. V2 must be divided by this value. Then we get a new value which is going to be corrected and which is going to fit the green line. When t is large, notice that the term 1 over 1 minus beta to the power of t will become closer to 1. So you'll be just dividing the v value by 1, and it's basically the same values. That's why you see the overlap between the two lines for a higher number of dates. So in this case, t is 2 for v2, and here we're considering beta as 0.98, and 1 minus b squared, beta squared is 0.0396, and we substitute this in this formula, v2 divided by this value, and that's basically the corrected value. Now we have seen the things that we need for the next types of optimization algorithms. The next type of optimization algorithm is gradient descent with momentum. This gradient descent with momentum uses the concepts that we have covered so far, such as exponentially weighted moving average, in order to compute the gradients and adjust the parameter. When our cost function is convex in nature, having only one minima, which is a global minima, as you can see, this function, this cost function, is a perfectly convex function. It is also known as ball shape, and if we put a ball here, then it's going to roll down naturally to the global minimum, as we only have one global minimum. In this case, we can simply use gradient descent optimization technique, and that will converge to the global minima after a little tuning in hyperparameters. So if we just use the previously given formula for gradient descent and repeat it multiple times, then we naturally find the global minimum. But the problem is, in real-world problems, the cost function has lots of local minimum. It is not going to be a perfect ball shape, and the gradient descent that we introduced before is going to break down and not find the global minimum, and it's going to find the local minimum, and it's basically going to stay there. So the purpose of gradient descent with momentum is to fix that problem. Imagine a ball, and we started from some point, and then the ball goes in the direction of downhill or descent. If the ball has a sufficient momentum, then the ball will escape from the whale or local minima in our cost function graph. So the name momentum was used here because it's basically similar to the momentum that we use when we talk about velocity, acceleration, and momentum in physics. So if the ball rolls down in a valley, then when you reach a local minimum point, if it has enough momentum, then it's going to escape that local minimum and rolls down until it finds the global minimum. So you can basically assume that the momentum term is going to help us to escape the local minimum. So gradient descent with momentum considers the past gradients to smooth out the update. So the previous gradient descent algorithms that we use does not consider the previously computed gradients when computing the new gradients. But by using exponentially weighted averages, we have seen how to consider the temperature for the previous days when computing the average for the current day. That's basically the formula for the exponentially weighted average. It computes an exponentially weighted average of the gradients and then use the gradient to update the weights. Instead of using just the currently computed gradients, we have to assume the previously computed gradients by using exponentially weighted average and add them or adjust the parameters. So this formula is kind of similar to the exponentially weighted average. So for the weight W, for the gradients dW, we are using the exponentially weighted moving average formula to compute the new gradients. So we use the previously computed gradients so far, and we multiply them by beta plus 1 minus beta multiplied by the new gradient. And we basically do the same thing for the bias, that's why we have dB. And finally, instead of using dW and dB to adjust the parameters, now we're using the newly computed VDW and VDDB for adjusting the parameters. Momentum helps accelerate gradient descent when we have surfaces that curve more steeply in one direction than in another direction. It also dampens the oscillation as shown in the figure. So gradient descent with momentum is going to help us to arrive to the global minimum much faster. The normal gradient descent algorithm is going to be it's going to have much more noise, because we're just basically computing each gradient one by one and adjusting the parameters. But while considering the exponentially weighted averages, this is going to be the average of the much noisier data points, because when we have discussed about exponentially weighted moving average, we have seen that the data points were much noisier, but the computed exponentially weighted average would be much smoother, and it dampens the oscillations in the figure. So we want the learning in the vertical direction to be slower, and we want the learning in the horizontal direction towards the global minimum to be faster. We can let our bias parameter to be B and the weights to be W. So when using the gradient descent with momentum, our equations for updating parameters will be the ones that we have seen before. And the implementation details by using pseudocode can be shown here. First, we can initialize VDW and VDB to 0. And on iteration t, we can compute the gradients first for the current mini batch. This is basically the same thing that we have done before. For gradient descent, we just use the dW and dB directly to adjust the weights, but now we're going to use the newly computed VDW and VDB for adjusting the parameters. And in order to compute the current ones, the current average is by using beta multiplied by the previously computed VDW, then plus 1 minus beta by dW, which is the current gradient. Then we'd also do the same thing for the bias. Then finally we adjust the weight W by the newly computed VDW, and we adjust the bias by the newly computed VDB. Notice that so far that we're using two hyperparameters. Those hyperparameters are alpha and beta. Alpha is the learning rate, and beta is the one that is used for the momentum. When using PyTorch, if you want to implement gradient descent with momentum, you have to provide the beta parameter, which is going to be the momentum term passed as an argument for the PyTorch function. If beta is equal to 0.9, as we have seen before, since we are dividing by 1 minus b to the power of t, we're averaging over the past 10 gradients. But in the case of gradient descent with momentum, we're not going to use bias correction. We have previously introduced the concept of bias correction so that we can align the values and adjust them so that they could not remain as 0. The next type of optimization algorithm is RMSProp. Here is a 2D contour plot for visualizing the work of RMSProp algorithm, but in reality there are much higher dimensions. So let's assume that this is our cost function, and in the vertical direction let's consider it to be the bias, and on the horizontal direction let's consider it to be the weights. We want the learning for our bias to be slower in the vertical direction and much faster in the horizontal direction. Gradient descent makes huge oscillation in its paths and takes long time and more iteration to converge because it contains big fluctuations in noise. So since we want to dampen the oscillation and we want the learning to be faster, such as the case in gradient descent with momentum, RMSProp is going to improve the learning in the horizontal direction from gradient descent with momentum. In RMSProp optimization technique, we update our parameters in such a way that the movement in the direction of the weights is more than the movement in the direction of the bias. So the learning in the horizontal direction, in the direction of the weights, must be much faster, and in the direction of the bias must be much slower. So basically what we're doing here is, in RMSProp, we're computing new SDW and SDB parameters. Notice we're using the notation as different from V, which was used for gradient descent with momentum, so that we don't have any confusion over the terms used. We can see that the dW previously was just a single value, but now we're squaring the gradients when we consider RMSProp. So the reason that we are squaring the gradients is we want the dW squared to be smaller, and we want the dB squared to be larger. So dB is already here a large value because of the large oscillations, and we're going to have, when we square it, we're going to have a larger term for the gradients. And once we compute SDB, here we're going to divide the dW and dB by the square root of SDW and SDB. So when we divide the gradients by the roots of the respective exponentially weighted averages, the update in the W will be more than that of the bias, because the term SDW will be much smaller when we're using small dW values. When we divide it by a small value, this is going to be a large value when compared to the bias, and the updates are going to be very fast for the weight. And for the bias, since we are using a large term here, for the dB squared, we're going to divide it by the square root of the SDB, which is computed by the exponentially weighted moving average formula. Since it's large, the division is going to give us a very small term, and the adjustment to the bias will be very small. And we also introduce an epsilon term, which is going to be added to the SDW when we divide the gradients. And this basically helps to avoid division by 0. So this allows us to take more large steps in the horizontal direction and converge faster, which is indicated by the green one. It also decreases the number of iterations to converge to the optimal value. We don't need a lot of iterations to converge to the global minimum. This gives the algorithm its name, root mean squared propagation. So the name RMSProp comes from the fact that we are using the root of the exponentially weighted moving average, so root of the mean squared propagation. So SDW and SDB are computed by using the exponentially weighted moving average, but the DW and DB here are squared because we want the DW to be much smaller and the DB to be much larger. But for the previous case of gradient descent with momentum, we can see that the DW and DB are not squared, and we're using the terms VDW and VDB directly in order to adjust the parameters. But here, once the exponentially weighted moving average for the gradients is computed, we're not going to use SDW and SDB directly, but we're going to divide DW, and here I need to make a correction for DB, by the square root of SDW and SDB respectively. Finally, we have arrived at the last optimizer, which is known as atom optimizer. It turns out that when we use momentum and RMSProp both together, we end up with a better optimization algorithm termed as adaptive momentum estimation. So ATOM is just an acronym for adaptive momentum estimation. Here, the first equation takes into account the momentum term from the gradient descent with momentum, which we have seen above, and the second equation is from RMSProp optimization algorithm. So this is basically the atom optimization algorithm. We're going to initialize VDW, VDB, SDW, and SDB from both the RMSProp and gradient descent with momentum as 0. On each iteration t, first we need to compute the gradients DW and DB for the current mini batch. Then we need to compute the exponentially weighted average for the momentum term by using beta 1. So we're computing VDW and VDB and adjusting them accordingly. The second, we use the formula from RMSProp and using another parameter beta 2 in order to find SDW and SDB. Finally, here in Atom Optimizer, we need to use the concepts that we learned from bias correction. So in gradient descent with momentum, we've seen that we don't need the bias correction. But here, after we computed VDW and VDB, we need to correct them by dividing them by 1 minus beta to the power of t. In the case of gradient descent with momentum, we divide it by the first hyperparameter beta 1, and in the case of RMSProp, SDW and SDB, we divide them by the hyperparameter beta 2. Then finally, we combine both into 1. Previously, we just divided DW by SDW, the square root of SDW, but now we're going to divide the corrected VDW by the corrected SDW, which is under a square root, and add the epsilon term, error correcting term, and we're going to update the weight and the bias. So basically what atom optimization algorithm is doing is by combining the concepts from both gradient descent with momentum and RMSProp in order to create a new optimization algorithm. Atom optimization algorithm performs very well in many different problems in deep learning. So in many cases, you'll see people use the atom optimizer more because it doesn't suffer from the local minimum, which was the case for the gradient descent algorithm. And it also doesn't suffer from the bias correction because we're using bias correction here. And it's going to benefit from both the momentum and RMSProp. Notice that we need to pass two hyperparameters to the Adam optimization algorithm. By default, in most deep learning frameworks, these hyperparameters beta 1 for the momentum term and beta 2 for the RMSProp term are going to be initialized to 0.9 and 0.999. But depending on the task, these values can be changed, and there are recommended values for a certain kind of task. The alpha was the learning rate, and this needs to be tuned. And finally, we have the epsilon term here. Finally, let's see how to implement a simple case of an optimizer by using a PyTorch code. In order to use an optimizer in PyTorch, you need to import torch.optim as optim first. Then you need to create a model. Let's say in this case we are using a linear regression model from the neural network package with a dimension of 1 by 1. And this 1 in 1 is just the number of inputs and outputs. And finally, we need to define a loss, and here we're using the simplest kind of cost known as mean squared error. So after defining the model and the loss, then we need to define the optimizer which we're going to use. In this case, we can choose the stochastic gradient descent, or we can use the Adam optimizer. The optim package has many different kinds of optimizers that you can experiment with. The first kind, if you use gradient descent or Adam, you need to pass the parameters from the model into the optimization algorithm. So what this is doing is, we have seen when we introduce parameters, the model.parameters method is going to contain all the parameters from the model because they need to be adjusted by the optimizer. And we also noticed that we need a learning rate for our optimizer because the formula for gradient descent includes learning rate, the parameters, and also the computed gradients. You might ask, where are the computed gradients? Here we're just initializing the optimizer variable. Then here we're going to start the learning procedure. And for I range epoch, for the number of epochs, we have mentioned before that we have to zero out the previously computed gradients before computing the new ones. And I covered this in detail in the videos that I made about gradients. But in that video, I didn't use the optimizer package here, the optimizer, in order to zero out the previous gradients. So you can just use optimizer.zero_grad function in order to zero out the gradients before computing the new gradients. First, we need a forward pass. So if you have an input, you can pass the input into your model, which is the model that we have created here, and assign it. And this, basically, the output from this function is going to be assigned to this variable. Second, we need to find the loss between the output and the target. The targets are going to be the labels, and the output is basically the output from our model. Remember that the variable name that you assign here is criterion, so you need to replace the loss function with criterion. Here it's a mistake. we need to use the same name, and you're going to pass the output from your model first and the labels second, and it's going to be assigned to a new variable loss. Once the loss is computed, we need to compute the gradients, and in order to compute the gradients, we need to call the backward function. So when you call the backward function on the loss, the computation graph has already been built, and the loss will be the final function. And when you call the backward, it's going to track the gradients for the parameters, and it's going to compute the gradients for each parameter. The final step is to update the parameters using the newly computed gradients. So in PyTorch, what you need to do is just call the optimizer.step function. The step function under the hood, what it does is using the formula for gradient descent to update the parameters from the model. So this is basically the workflow on how to use the optimizer. In the next video, we're going to see in detail how to implement optimizers using a simple model. We're going to use NumPy first, and second, we're going to use PyTorch in order to understand what's happening behind the scenes. As you can see, PyTorch is basically doing most of the work under the hood. You basically need to be familiar with which functions to use when training the model. First step, creating the model. Second step, creating the loss. Third step, creating the optimizer. This is going to happen over and over again in future videos, so you need to memorize this part. Then when you start training the model, you need to define a loop, and inside the training loop you need to zero out the gradients first. Then you get the output from the model. This is forward pass. Then you compute the loss using the loss function defined here. Then you compute the gradients using the loss.backward method. Then don't forget to call optimizer.step, which basically performs the formula for gradient descent over each iteration. So you need this formula to be computed. If you want to use other kinds of optimizers such as RMSProp, you just need to change the name from SGD to RMSProp. Congratulations for making it this far in this video. There are lots of optimizers to choose from, and knowing them and how they work will help you to choose an optimization technique for your application. I hope you found this video beneficial, and in the next video we're going to see the implementation in detail.
Audio Jungle.